Hello and welcome back. Year 13 revision again today, but no integration. Today is going to be trigonometry, okay? Best way to revise trigonometry. The best way is by far by practicing the type of question that you have to prove a trigonometric identity, in my honest opinion, okay? So I've got up there quite a few. I'm going to go through as many as I can, probably in about 30 or 35 minutes. I've got a total of 40 questions, 40. No way I'm going to do them in one go, but I'll give it a good go over probably 3 lectures to actually show you the basics, okay? So I don't want to be wasting time. I'm going to go straight away into the first identity. First identity is to prove that the sine of x plus pi over 3 minus root 3, I can barely see there's a cos, I think, cos of x plus pi over 3 is identically equal to 2 sine x. How do we attempt questions like this? My advice before you start attempting this type of questions, to draw a list like your own formula booklet that lists all the important trigonometric identities, and this includes the Pythagorean group, the double angle, the compound angle to start with, and of course I assume you know all your definitions, like what is a sec, what is a cot in terms of sines and cosines, and so on. So when you're attempting this, okay, these are non-important identities, sort of secondary identities, is to actually refer to that booklet of yours and try to depend less and less as you're going along, okay? Because this is not just about learning by heart these identities, but it's also about having working knowledge, being able to see things within the algebra, basically, okay? So the way we attempt these questions, first of all, we start from one side and we go to the other. So usually it'll be the left hand side and we try to go to the right, okay? So what's there on the left? Well, quite clearly we got the sine of a plus b and the cos of a plus b. So LHS, we're gonna go for the compound angle for sine, so that's gonna be sine x cos of pi over 3 plus we're gonna have the cos of x this time times the sine of pi over 3, and we're going to the second term of the left hand side. Let's not forget the minus root 3, but I'm gonna cheat here, and what I'm going to do, the cos of a plus b will produce 2 lumps. I'm going to multiply them simultaneously with the root 3 and also take care of that minus so I don't make mistakes in there, okay? So you have to be very careful to what I'm doing in there. I'm going to save myself a line. Probably I'm a bit naughty here. So cos, sine, sine for this. So it's going to be the cos of x, the cos of pi over 3, and the cos, the second term, the sine term, will have a minus, but don't forget I've got the minus from the minus root 3, so it's going to switch to plus root 3 sine x sine pi over 3. So now what? It looks very, very messy, but let's not forget the cos and sine pi over 3 that it appears several times within this expression is a number. We can use a calculator, or perhaps we know it. So what I'm going to do, using my calculator, cos of pi over 3 is a half. So that's a half times the sine of x. The sine of pi over 3 is root 3 over 2, lots of cos x. Using my calculator again, and let's not forget we got a root 3 here as well. The cos of pi over 3 is a half. So that's going to give me minus root 3 times a half, which I can write as root 3 over 2, lots of cos x. And here, what happens here? I've got the root 3 at the front, and the sine of pi over 3, it is actually root 3 over 2 of my calculator. This will give me a 3, so that's going to be plus 3 over 2, lots of sine x. This middle bits will cancel, and of course I'm going to get the 1.5 plus half is 2 lots of sine of x, which of course is my RHS right hand side, and identity is proven. So that's the general technique for doing this kind of work. So I'm going to go into question number 2. Question number 2, so that was number 1 on my list there, is I'm going to get out of the way because I can barely see the sheet from there. Tan theta plus cot of theta is identically equal to 2 lots of cosec of 2 theta. Okay, just double checking I've copied it correctly. Left hand side or right hand side? Perhaps we can do it from the right as well, this one. I want to give it a go, but it's not natural because, okay, what we're going to do with this? The reason I say I can do it from the right, probably I can see it all the way from the left and then I can play it backwards to you, like in reverse if you want. So so if you were to go from the right, just to give you an idea what's going to happen in there, I'm not going to do it because it's not sensible. The 2 cosec, you can write it as 2 over sine of 2 theta. Then you can write this as 2 over 2 sine theta cos theta, which of course the 2's will cancel. And then what do you do for something like this? Now this is the sticking point, is to recognize that, you know, this 1 is no 1. It's no 1, no shit. What is it? It's actually a cos squared theta plus a sine squared theta. And then if you split your fraction from here, you will get the left-hand side, but it's not sensible. It is not natural to be doing anything like that. So we'll start on the left, because when we have 2 items as a sum or a difference, of course, much easier. We can add stuff. So let's see. Let me use blue pen perhaps for the workings. Try to keep to a uniform color scheme for once. So left-hand side, tan theta plus cot theta. Let me just write it again. Tan theta plus cot theta is equal to, because the other side has a cosec, which is a sine. I didn't have to actually put a c there. Cosec of 2 theta. It's probably a good idea to switch into sines and cosines. So sine theta over cos theta plus the cos of theta over the sine of theta. And now what do we do there? There's not much to do but to add the fractions. What else can we do in there? Okay, common denominator, cos theta, sine theta, and on the top, timesing it across, it's going to give me, and it looks good already because I got a sine squared plus cos squared theta, which of course it'll give me a 1 over cos theta sine theta. At regular intervals, it's worth looking at your right hand side and say, okay, am I getting there? Does it look good? When will I know I've got there? Basically when I get 2 over the sine of 2 theta, and the sine of 2 theta looks something like that. I'm missing a 2, no problem. I'm gonna double top and bottom, 2 over 2 cos theta sine theta. There's my 2. This is of course not by definition, by an important identity, the sine of 2 theta, which is 2 times the cosec of 2 theta, which of course, I don't know if you can see my writing now, RHS. And number 2 is done. Okay, let's see if I can fit number 3 in here. So I'm going to make some space, so rub off number 1. Number 3 is an important kind of technique involved in this one, which you really need to start spotting. We're going to need now the double angle identities for this one. We're trying to prove that 1 minus the cos of 2x over the sine of 2x is identically equal to the tan of x. Well, quite clearly we're going to start from the left. Okay, and some observations. If you look on the left, we've got double arguments there, or if we look on the right, single argument. So quite clearly we're going to need to break the 2x's into x's at some point. I'm not copying the left hand side, which is that, I'm just looking at it. So on the fraction that I've got there, the denominator, I've got no choice. 2 sine x cos x. There's nothing else I can write for it. What about the top? 1 minus, and I have now a bracket. And the problem with the cos of 2x, there's actually 2 problems. First of all, it has 3 versions, which I must know. And secondly, all 3 versions resemble other identities. So you have to be very careful you don't make a silly mistake. So I've got a version that has a sines only. I've got a version that got causes only. And I got a version that has causes and sines. So which of the 3 I need in there? And the answer is none of them. Well, it's a bit of a sneaky answer I'm giving there, perhaps, because it's one of them. But I'm phrasing it the wrong way. Do I need the sine only, the cos only, or the sine and the cos? The answer is I need the one that cancels this one. So if I'm gonna write up here, what's the cos of 2x? I've got one version that says that is equal to 2 cos squared x minus 1, and I've got another one that says 1 minus 2 sine squared of x. Okay, so if you look what needs to slot in there, is the second one, because once I put the 1 in there, it will cancel it. If this one was a plus, incidentally, it was 1 plus the cos of 2x over sine x, I would have needed the first one. I would have needed the one with a minus 1 in there, because if that was a plus, I would have needed there a minus to cancel it. Okay, we don't have this scenario, so let me just rub it off, and I'm going to rub off these identities as well from there. That of course is a minus in our case, and the identity we need for this one is 1 minus 2 sine squared of x. So now we tidy up. 1 minus 1 cancels, and I end up with 2 sine squared x on the top over 2 sine x cos x. The 2's will cancel. I'm going to also lose the square from there and the entire sine from the bottom, and I've got a sine x over cos x, which of course, looking on the right hand side of what I'm trying to prove, is of course my requirement. Okay, it is not just important to know all your identities by heart, the ones that I said to you in the beginning to make a list, but you must also be able to see stuff when you're doing your work. So you got to have working knowledge. Just knowing them by heart, like you're learning your lines to a play, is not going to get you anywhere. So question 4, the identity this time is the cot squared of x over, is it 1 plus cot squared? I cannot see it. It's 1 plus cot squared of x. And what is that identically equal to? I think it says cos squared x. Okay, we start from the left again. Some observations. What choice do we have in here? I hope we can see this identity here. 1 plus cot squared x, of course, cos x squared x is definitely, it will simplify things. Maybe we can switch into sines and cosines afterwards. Okay, so that is the first observation. The second choice that we have is to switch everything into sines and cosines. That will also work. So we're gonna go, first of all, I'm gonna do it 2 ways. I'm gonna do it because this is, I think they're both okay for this particular one. So some students spot that immediately, so they will go LHS is equal to the cot squared of x, that's on the numerator, and they realize this is the cosec squared of x. What's my next line? Well, my next line quite clearly is perhaps to switch into sines and cosines. I'm going to create a double fraction. Personally, I'm not scared of double fractions, but I think there's probably a better move to do to avoid that. I'm going to write the cot squared of x as it is, and you know this cosec squared of x at the bottom, I'm going to shift it to the top. But if it shifts to the top, it changes name, and its name of course is sine squared of x. Okay, it's reciprocal, because sine is 1 over cosec and cosec is 1 over sine. Now I'm going to switch into sines and cosines, so I have a cos squared x over a sine squared of x times a sine squared of x, and perfectly give me cos squared x, which of course is my RHS. Okay, I think this step is much nice to actually do, because it avoids mistakes. I did say it can be done if you go sines and cosines. I'm going to do it here. I'm going to be a little bit messy, so ignore, obviously that's our answer. If I switch straight away into sines and coses, I'm going to create a double fraction, but bear with me because it's important to actually see this as well. I'm going to have there a cos squared of x, that's my cot, over a sine squared of x. What I'm going to do, actually, I'm going to rub off the bit from above because it's distracting us as well. And I'm going to have to rub it off at some stage anyway, so I might as well do it now. So that's the workings for number 3. So we can see that a little bit clearer. So that's sine squared of x. And at the bottom I've got, of course, exactly the same thing, 1 plus cos squared x over sine squared of x. So the question now looks quite scary, but it's not. There is a technique when it comes to this kind of, usually it comes in trigonometry, but it comes in other kind of like places where we can simplify double fractions very, very easily. I'm going to multiply top and bottom of this fraction by the same quantity, and I'm going to actually write it here so you can actually see what I'm doing. Is by sine squared of x. Remember the 3 lumps, 1, 2, so there's another one to be multiplied by sine squared of x, which of course the one on the far left. What happens here is now everything collapses, because if you see what happens, the sine squares will cancel. So on the top I've got cos squared. At the bottom left I'll have a sine squared of x, of course, and this will also cancel here, so that leaves me a plus cos squared of x. This is an identity, of course, is equal to 1, which of course it'll give me cos squared x, which again is RHS. So this is actually can be done even if you don't spot that this is cosec squared of x, which you should. It can be done very, very quickly. Okay, we're done with number 4, so we're gonna look now at number 5. Number 5, fraction. We have tan x sec x over 1 plus tan squared of x. And what does that give us? That simplifies to simply a sine of x. Okay, some initial thoughts. First of all, definitely we're starting from the left. Very complicated, we can make things happen. What are the things, what are our options? Well, I can switch everything into sines and cosines, definitely is an option there. I can, if we look at this denominator, maybe we can spot the identity 1 plus tan squared is equal to sec squared, and I think that's vital to actually spot this one, although it can be done if you switch into sines and cosines. I'm going to do it both ways again, this one, just to show you the little variants, the little tricks. So student number 1 starts with LHS, student number 2 starts with the same LHS, left hand side of course, and they proceed different way. This student spots that this is in fact an identity, so he writes that's equal to tan x sec x, the whole thing, over sec squared x there, sec squared of x. Immediately for him things happen, so you can lose the sec from there and the square from there, so he has a tan x sec x. What happens next? I'm going to switch into sines and no, sorry, I'm writing stupid things there, beg your pardon. Okay, so that's the tan of x, the sec is at the bottom. So what do I do next? Okay, I could switch into sines and cosines straight away. I'll create a double fraction, so it's probably better for this particular one to write the tan of x as it is, and this sec, move it to the top. But if I move a sec to the top, like in the previous example, this reciprocal is a cos, so it becomes a cos, so the sec is now a cos. What happens next? Now we're going to write this as sine over cos, sine x over cos x for our tan, times the cos next to it, it will cancel, sine of x, RHS, done. The second student didn't actually spot that this is an identity, so he switches straight away to sines and cosines. I don't think it's that bad. So for him, the tan has become a sine of x over a cos of x, and the sec has become a 1 over cos of x. Looks very scary already. And he has the 1 plus a tan is a sine of a cos, so sine squared of x over the cos squared of x. Okay, playing for a little bit of time just to see what we're going to do. Let's multiply the numerator. So we're going to take our time with this one before the kill. So sine of x, cos squared x, and then we have 1 plus the sine squared of x over cos squared of x. Remember what I've done earlier on. I'm looking at this And I'm just thinking now that will actually clear if I multiply top and bottom of this fraction by one very special quantity, and that quantity is the cos squared of x, because it will cancel me here, it will cancel me here, and of course here it will leave me alone as I am. So that's a cos squared of x, and let's see what happens. That's actually not that bad at all. If you see what's going to happen, the cos squares cancel there, so I'm left with just sine of x on the top, and on our denominator, sorry, it should be a cos squared of x, that's this bit here, and I'm left with a sine squared of x, which of course this is a 1. It gives me sine x, which is again RHS. So it's important, and I picked these identities. I have a list of probably about 100 plus, and I picked those because they illustrate some nice techniques. None of them is actually that hard. The identities I chose, they'll be getting slightly harder question upon question, hopefully, but if you know, and if you're trained and you know your identities, your important identities, that is, well, you should be able to follow pretty smoothly what is going on, and eventually of course improve. I'm gonna move that here to copy because this is getting on my nerves by now. Identity number 6. 6 is kind of like look longish and very scary looking to start with, but I don't think it's gonna be that bad. It doesn't scare me. Sec squared of theta cos to the 5 of theta plus cot theta. They call the whole family, I think, this cot theta, a cosec theta. Who's missing? There's more. Sine to the 4 of theta. Okay, I get it. Is identically equal to cos theta. Okay, let's have a look at this. Definitely left hand side. I'm gonna use this black pen for this one. I can't be bothered to switch into black and blue. We can switch into sines and cosines. All of these are just sines and cos. I don't know if you're aware of that. If you think about your trig functions, they can always be written in terms of sines and cosines, each and every one of them. Okay, so that's an option, particularly because my right hand side is a cos. Hopefully the things will cancel. But before I do that, I'm just wondering if there's anything else I could do in there. I'll just check I copied it correctly just in case. I got cos to the 5, sec squared, a cot, a cosec, and a sine. Okay, sec squared and cos to the 5, the reciprocals of one another. So yes, probably I will switch into sines and cosines as my first step. So 1 over cos squared theta, that's the sec squared, times the cos to the 5 of theta next to it. The cot is of course a cos theta over sine theta, times the cosec. The cosec is a 1 over sine. I hope desperately for some cancellations, and some of them will take place. I'm not going to be showing in between steps. I think we should be able to see some obvious cancellations. So first of all, the cos squared of theta will cancel that, and it will change it into a cos cubed of theta. And on this particular term, if you look, I've got a sine squared at the bottom. If I was to times it out, I'm not. So I've got sine of theta times sine of theta, sine squared of theta. And this sine squared will cancel the sine to the 4 into a sine squared of theta on the numerator. You can of course put the extra line. I'm not doing it on the board here. I do apologize. So what will remain after all of this is a cos cubed of theta, this bit here. And from this, let's not forget this cos, which is still there. Cos theta times sine squared of theta. And now we're looking at this and say, okay, what else is there to do now? It has simplified greatly. I've got a common factor of cos theta that I can pull out. And once this is done, it's going to leave me with a cos squared of theta from the cos cubed, plus this has gone out, a sine squared of theta, which of course this is one identity, which of course leaves me with cos theta, which is the required answer, RHS, which is what I was trying to prove. So that was question number 6. I'm going to put the number 7 here. Probably that's a better board layout to do it like this vertically. What does it say? It says cosec squared of x multiplying a tan squared of x minus a sine squared of x. Lots of squares for this particular one. Turns out to be identically equal to the tan squared of x. Okay, let's think about what we're going to be doing with this one. Lots of squares, so we should be thinking quite a lot about a Pythagorean group of identities, or the squared identities as sometimes they're being called. The 1 plus tan squared is sec squared, 1 plus cot squared is cosec squared. But there's nothing of this sort in there just yet. Maybe it will not appear, maybe we won't have to do anything like that. We'll have a bracket. This thing is not special. The tan and the sine, they're not connected in some direct way when they're squared. So probably what I will do in there is I will multiply the bracket, fairly sensible, and then probably, unless I see something obvious, I will switch into sines and cosines. So left hand side, multiply bracket, here we go, and now of course I see something special straight away. This is my cosec squared of x times the sine squared of x. Why is it special? It's because this is 1. This is 1 because, of course, a cosec is 1 over sine squared times the sine squared, gone. So that's quite interesting. Okay, so can I do a couple of things at the same time, because I'm not quite sure what to do with this. So probably, so I don't waste a line just to write this 1, I might as well manipulate this at the same time. I will switch into sines and cosines. So 1 over sine squared for the cosec squared, 1 over sine squared of x, times, and that looks good as well, nice, isn't it? We've got another cancellation take place, and this is the 1. So what have we got in there? We end up with 1 over cos squared of x minus 1. From here, there are 2 ways to proceed. Both of them are fine. It's kind of like the same thing, really. It's just written and expressed in different ways. Some people might they might add the 2 fractions, because that's a 1 over 1. So this will simplify to 1. If you put it over the same denominator, which is cos squared, it will be 1 minus cos squared on the numerator, which of course on the next line will be a sine squared, and sine squared over cos squared will give you a tan squared, which we're trying to prove. And there's a second lot of people which they might, I did say in the beginning, this probably will have some Pythagorean identities in it, too many squares in there. So the 1 over cos squared, you can actually write it as sec squared of x minus 1. That's writing the 1 over cos to sec squared. And then in an exam, I wouldn't just write that this is equal to tan squared of x, because it is. But just in case the marking scheme says the examiner, or marker shall I say, must be convinced, then we'll lose marks on technicalities. So for something like this, if you're in an exam, if I was in an exam, definitely I would write this is equal to the tan squared of x, which is equal to our rate says. However, I would write a little explanation for the marker to say, you know what, 1 plus tan squared of x is equal to the sec squared of x, and therefore it's obvious what I'm doing in there when I'm writing from there to there. And I will refer to this line perhaps as well, just in case they just think I am cheating there. Okay, we are with number 8 next. Number 8, does it look hard? A little bit unusual, this one. The tan of 2 theta. Again, just bear with me, I'm going to get out of the way if I'm covering the question. Tan theta sec theta is identically equal to 2 sine theta sec squared of 2 theta. That doesn't look too nice. It doesn't look too nice for one, to me that is, for one simple reason. The simple reason is both sides have single and double arguments at the same time. So I've got a 2 theta here and a theta, and I've got a theta and a 2 theta there as well. So it might not be clear what double angle I need to break down to create thetas, or what do I need to be changing as I'm going from one side to the other. The next question is, do I start from the left or do I start from the right? Sometimes you need to develop a bit of a mathematical gut feeling and just get a feel for the question. And I will also tell you, but don't take my word for it, in an exam they will tend to actually, if a question is equally complicated from both sides, they will try to actually write the sides most sensible to start from on the left. So if that was the side that they want to start from, probably would have written it back to front. So we're gonna start from the left and see what happens. There's another thing to notice in there. This is for the people that think a little bit far ahead and they can actually get an insight to the question. I'm looking at the 2 thetas on both sides. The tan of 2 theta is sine theta over cos 2 theta. Cos 2 theta. Okay, this is a cos of 2 theta here, if you think about it. So what that tells me is says to me, possibly, after I write this tan of 2 theta as sine over cos, that cos of 2 theta, I'm going to move it to the top as a sec 2 theta, and it's going to be with me to the bitter end. I'm not touching that again, okay? Anything else I'm going to need to kind of play with, but not that one. So left hand side, let's go and let's see what happens. Change the tan into sines and cosines. Times the sec. Yes, 1 over cos. Because I noticed this sec of 2 theta, which is here, what I'm going to do is I'm going to write, first of all, the sine of 2 theta now. There's no more 2 thetas on the right hand side, so I need to break the sine of 2 theta. So that is 2 sine theta cos of theta. This is this lump here. The cos of 2 theta, I'm going to move him to the top next to this expression, but now it's going to be called the sec of 2 theta. And this particular one, if you think about it, because it is a part of this will cancel with the cos that I've got in there, I'm going to leave him as he is. It's good to be like this. So what happens now? This lump matches what I need to have on the right hand side, and if you look at the rest, it's all there. The cos of theta and the cos of theta will cancel, so all I've got left in there is 2 sine theta multiplying the sec of 2 theta, which of course is my RHS. What do I think about this identity? I think this identity, once you spot a couple of things, it's actually dead easy. But if you don't spot, you could be chasing your own tail and never catch it. So it's a little bit sneaky. I wouldn't have liked to have this under exam conditions and perhaps under pressure. Okay, let's go to question number 9 and let's see what's on number 9. 9, another fraction. So we're gonna start from, actually no, I need to write the identity first. Let me just write the identity because I need to see, well, first of all, what it says. Cosec of theta over cosec theta minus sine theta. That's the left hand side of the identity. And what is that equal to always? Apparently this is identical to sec squared of theta. Start from the left, of course. There's a few things we can do from the left. Maybe write into sines and cosines, simplify the fraction, might be able to split it in the future. Maybe we can see other identities. Sec squared, what can I do from the right? Perhaps write as 1 over cos squared. I can write as 1 plus tan squared. Not a lot of things. I can see how to go from there to there. So I'm going to start from the left because it gives me more options. And I'm going to write everything in sine and cosine. So 1 over the sine of theta, numerator, 1 over the sine of theta minus sine theta. We've seen this theme with expressions like that twice in this particular lecture, and therefore this double fraction, if you want, will simplify if I just stick a sine theta top and bottom. So that's the rules of fractions, of course. and a lot of things will cancel. Boom, 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 and that's gonna become a 1 minus sine squared, which is very, very nice. So on the top, I've got 1. That's the 1 from this fraction. On the bottom left, 1 minus sine squared, and I think now we should be able to just finish it off from there, because of course that is a cos squared at the bottom, of course, and a cos squared theta is a sec squared theta on the top, which of course is RHS. That's rather nice. Okay, so this technique, which we've seen now so far 3 times, it's kind of useful to simplify stuff. So I advise you to when things like that occur, not to be scared and try to kind of like get better at it. Integral, because I'm doing so much integration at the moment. That was number 9, by the way. So number 10 coming up. So identity number 10, loads of squares again. So we've got, it's not practically the same. Yeah, that's the mirror image of number equivalent statements, like the number 7. I didn't spot it, otherwise I wouldn't have put it there. I'll do that as number 10. Let's do it again. I'll do it a little bit fast this time. Okay, if you look at number 8, if you wrote it down and you look at no, number 8, number 7, I beg your pardon. If you look at number 7, the one I'm doing now is the same thing really. Cot squared theta minus cos squared of theta, and this is identically equal to a cot squared of theta. All right, we're going to start from the left. The last one, I think number 7, I've done it a couple of different ways, so I'm just going to do it one way. What I'm going to do, I'm going to multiply the bracket. Sec squared times cos squared, they're reciprocals, they will give me 1. So this will give me a sec squared theta cot squared theta minus that times that is 1. Do some workings on the side if you cannot see it. Then I'm going to switch into sines and cosines. So the sec squareds, of course, a 1 over cos squared theta. Cot is a cos squared theta over sine squared theta. Still a minus 1. The causes will cancel. The squared, cos squared rather. And what I'm left with is 1 over sine squared of theta minus 1. And I've done it 2 different ways. I wrote it as a fraction, the last one, and then the other one I used the Pythagorean identity. For this I'm going to use the Pythagorean identity, and I'm going to write it as cosec squared of theta minus 1, so that's the 1 over sine squared. This is an identity. The last time I said to you, write that is equal to your answer and put a little explanation. This time I'm going to do slightly different, because I can't be bothered to write an explanation. So a cosec squared theta will be equal to 1 plus cot squared of theta, fact, that is the same as that, minus 1, which of course the ones will cancel, and that is of course a cot squared theta, which is my RHS. Question 10 done. Question 11 coming up next. That's a little bit different to everything we've done so far, so hopefully we'll learn some new techniques, some new tools. 11 is 2 fractions to be added. The cos of 2x over the sine of x plus, kind of symmetrical, the sine of 2x over the cos of x, and apparently that is equal to, identically equal to the cosec of x, and we're trying to prove the validity of this trigonometric identity. What can we do in there? Some observations first of all. We got double angle on the left and no double angle on the right, so definitely somehow we need to lose this double angle. We also have a fraction, so we have options of adding as well. So how shall we proceed with something like this? I'll be inclined to break the cos of 2x and the sine of 2x and just see what happens. So I'm going to start from the left, and I'll show you afterwards a quick way of doing this, completely different idea altogether. Left hand side, something over sine x plus something over cos x. The sine of 2x is rather nice because it can only be 2 sine x cos x. The problem is this cos, which is very, very annoying. So what do I put for that? You know, if I had a 1, we can make choices here. It's not that straightforward. So what I'm doing is I'm not doing anything. I just left this blank. I want to think about it, and I proceeded to look at this, and of course that on the next line, of course, it'll give me plus 2 sine x. Okay, so 2 sine x, so whatever this produces plus 2 sine x should give me a cosec. So that is telling me that somehow I need to cancel that, because I don't think I'll be getting the cosec of x from this. So there should be a minus 2 sine x from this simplification. I can kind of see now what I need. If you can't see it, you have to perhaps play around, put either your 2 cos squared x minus 1, put both of them in. Eventually it will work. It will just, at the moment I'm actually showing you the quickest way that it will work with some justification. It might not be immediately obvious to some of us. So if you look at what I'm doing, this is my cos of 2x, the one I picked. And now look what happens. After I simplify that, I have a 2 sine x. When I split the fraction there, look at this. This is where I was looking, and that's why I picked this one. I'm going to have a minus 2 sine x. That's by dividing that by that. But of course, at the front, I'm going to have this ugly 1 over sine x, which is not ugly at all, because of course, that will be my answer. This is in fact my cosec of x, which of course will be the RHS, right hand side. I did say identity will get a little bit harder to see. The ones that I picked are kind of like are useful to show you some techniques. By the time we do another perhaps 5 or 6, they will get quite involved. So I'm going to show you something else for this particular one, because it can be done in another way, which is not obvious. If I start from the left hand side again, but this time I'm not thinking at all about double angle. It's not natural not to think double angle there. It's to think about adding the fractions. Look what happens if I add the fractions there. I'm going to get a common denominator of sine x cos x. All good, okay. So what will happen there? A mess is what's going to happen. A cos of 2x multiplied by a cos of x, that across, and then plus a sine of 2x multiplying a sine x. Most of us would have given up by now and say, what a stupid thing to do. This is a mess. But it's not a mess. You just need to recognize this thing here. If you think about, I'm going to write it here, the cos of 2x minus x. That's your a minus b. What happens if I expand that? I'm going to get cos cos plus sine sine. Cos of 2x, cos of x, plus now the sine of 2x times the sine of x. This in fact is your cos of 2x minus x over sine x cos x. And this of course is just simply the cos of x if you want. I'm going to write it here. Cos of x over that. Cos is gone. 1 over sine. I'm not going to write it. It just merges after that. It's 1 over sine, which of course it will give you the same right hand side. Okay, and I'm going to do one more, I think. Number 12. And we'll finish it probably with this one, because it's getting I was hoping to be doing a lot faster. I thought trigonometric identities are much quicker to do than integrals. They're in fact just as time consuming. So totally misjudged the amount of time they take. Maybe it's me waffling on, maybe it's me explaining the obvious to most of you can understand and say, come on, move on, move on. Okay, that's our last one for today. Number 12. 1 plus tan squared of x over 1 minus the tan squared of x is identically equal to sec squared of 2x. Okay, what do I do with this? left hand side or right hand side? I would have liked to have started from the right hand side because I like to break double angles into single angles, but what do I do with the sec of 2x? On the left, some good things. Is there any obvious identities? Well, this is an identity. 1 plus tan squared is equal to sec squared of x, but on the top it doesn't help me as much as it would have been helping me if it was at the bottom, because at the bottom I could have split the fraction. Here it doesn't really help me. So where do I start with something like this is the question, okay? So where do I start is in fact probably start on the left and probably start with the most basic technique of all, which is sines and cosines. So let's go. Left hand side. Okay, 1 plus sine squared of x over cos squared of x over 1 minus sine squared of x over cos squared of x. We've seen expressions like this a few times tonight, okay? And we shouldn't really be getting scared of things like that. Things like that simplify very nicely, very quickly. I cannot really fit the whole cos squared on the double fraction there, but what I'm going to do is I'm going to multiply. There's 4 lumps, 1, 2, 3, 4. Each and every of these terms, if you want, of the double fraction, it be times by the cos squared, because if I do that, everything will cancel. So if I times the 1 by cos squared, it'll give me just simply cos squared. If I stick a cos squared here, cancel, cancel, plus sine squared of x. That's good because that's of course 1. What happens on the denominator? Times the 1 by cos squared is again cos squared, times this by cos squared here, cos squared and cos squared of x, gone, minus sine squared of x. Okay, so that's good because there's a lot of simplification, much nicer than the line above, and also I've got the numerator now of 1. So let's just take an extra step now. Cos squared x minus sine squared x. And now probably I hit a brick wall. But I kind of know my identities, and even if I don't, I'm just wondering, could that be something else? I mean, how will I know after all when I'm done, when I'm on sec squared, sorry, not sec squared, sec of 2x. So my target, of course, not sec 2x. My target should be 1 over cos 2x. Once I'm done, I've got this, then I can say is equal to that is equal to RHS. So I've got 1 over something. So the question that I've got to ask myself, is that perhaps a cos of 2x? And the answer is yes, it is. That's why I say you really need to know your identities. This is in fact one of the 3 versions of the cos of 2x. It's not the most used one, okay? So this particular one, we don't use that as often, and perhaps we don't remember it. And it also resembles another identity, it resembles that, but that's actually the cos of 2x. And from there now, I've already written it. That's of course that which will lead into a sec of 2x, and of course that will take us to the right hand side. Okay, so that is the end of this lecture. I hope you just got quite a few ideas and a few things, and I hope you understand that you really need to learn your important identities and then practice with them. Okay, so I'm gonna put I hope to put another 2 lectures, otherwise it gets a bit tedious to watch, and practice yourself. Okay, so keep practicing. And who's laughing now? We're definitely laughing. I think we're getting better in trigonometry. Just keep going like this, guys, and I'll see you very, very soon. Bye for now.